It might not give you a global maximum, but it will return you a local maximum. So it is not ever going to give you an optimal solution. One important fact about hill climbing algorithm under the local search algorithm is concerned, it is not guaranteeing you an optimal solution, but it is guaranteeing you a solution that is existent in the given local state space that it can navigate. Okay, so local maximum solution will always be given to you, so you are going to get a suboptimal solution, and we are okay with that. Why we are okay with that, we'll talk about this in the second lecture of this particular topic. Now, what are the inputs? The problem is the input. Certain variables it is going to use. Number one variable is current and the other one is neighbor. Okay, these two variables, remember that these are not static variables. तो एक कॉल के बाद ये वेरिएबल आप भूल जाओगे. These are not static variables. तो ये over the different calls of hill climbing function are not going to stay with the algorithm. Okay, first step in the algorithm, make a node. Initial state of the problem को access करो और उससे node generate करो. Node data state generate करो. Node data structure मिलने के बाद उसको current variable में store करो. And then there is a loop. What this loop is doing? This loop is actually finding a higher valued successor of current node. Current node का को वो inspect करेगा, वो apply करेगा transition model, find out करेगा what are the next state. From the next state, it will pick up the node with the highest value compared to current node. Okay, जो भी मेरे successor nodes है उसमें से highest valued node कौन सा है वो pick up करेगा with respect to certain cost function obviously. If it is a hill climbing problem, I am trying to get my maximization of the profit. तो profit criteria होगा कोई, happiness criteria होगा कोई, तो वो profit criteria को maximize जो करेगा ऐसा child node को आप neighbor variable में store करो. So I have in current variable current node, the initial node initially, then in neighbor variable I have the highest valued successor node value with respect to the profit criteria if it is a hill climbing problem. I'm trying to navigate to the top of the hill. Okay, now I have two nodes, one is the current node, one is the neighbor. Neighbor is the immediate successor with the highest value. Okay, so we will check the value of neighbor against the value of current node. If value of neighbor is less than equal to value of current node, then return current state. Means what? Current state बेहतर है neighbor से. अगर neighbor का value कम है current state से, it means that if this is the current node and possibly this is the neighbor node, okay, the height of this neighbor node is definitely less than the height of this node. So my current node is a better solution. Return that. Otherwise, return this. Okay, that is exactly what it does. I am updating current node if the neighbor node is better than the current node with respect to obviously certain criteria which is stored in this value variable, which is stored in this value variable. Okay, we will be talking about rest of the things. Yeah, we can actually. Okay, hill climbing search has certain issues. So this is a state space state space projection or a 2D landscape. एक लैंडस्केप है जो हिल क्लाइंबिंग लैंडस्केप है जिसको 2 डायमेंशन में प्रोजेक्ट किया गया है. The x-axis is nothing but representing the state space and the y-axis is representing the objective function value. Now, what is objective function value? Objective function value is this value. मेरा जो ऑब्जेक्टिव है जिसको मुझे मैक्सिमाइज करना. So I'm trying to do what? I'm trying to maximize my profit. To go to a hill top means maximizing my profit. You can relate to it. So every time, every state will have certain function f to which that state we will apply and we'll get a number. And that number, say suppose that number is m, that is this value. Okay, and we are trying to maximize the value. This is what we are trying to do. So this is my state. So initial state I'm putting as fs. So f of s we are applying. This is we are evaluating the value of state s, or what is the happiness that I have being in state s. This is what we are trying to understand, and that will be a number, and that number is represented by this value variable. Okay, say that number is m, and what we are trying to achieve is we are trying to find out a state for which this m is the highest value. That's all the algorithm is doing. Simple algorithm, and this is what exactly that algorithm does. So this objective function tells you if I were in the state Si, what is the value of this function f. So what is the value of f Si? This is what this particular graph is about. So every point on this graph, this continuous line is there, but every point, if I divide this into if I discretize this graph by showing certain points like this, sorry, I should use a straight line like this. Okay, then the x-axis would be some s of j, state j. So this is some state. So this point will refer to certain state Sj, being in a certain state Sj, and this particular y-axis would be f value of Sj. Okay, this is the objective function. Now in terms of hill climbing search, this is referred to as objective function. इसको पहले हम लोग जब इन्फॉर्म सर्च एल्गोरिथम्स देख रहे थे, इस पर्टिकुलर फंक्शन को हम लोग इवैल्यूएशन फंक्शन f के तौर पे देख रहे थे. Okay, which was h of n in case of greedy search, which was hn plus gn plus hn in terms of a star algorithm. Okay, so it is one and the same thing. Some way we are trying to identify what is the objective value at a particular state. Now see, if you see this this particular state space, you will see certain issues in here, and those issues are, so this is the global maximum. So if I want a maximum value of fs j, then or f value, so f value का maximum जो value है वो यहाँ है पूरा का पूरा लैंडस्केप में. पूरा का पूरा ये जो लैंडस्केप है, इसको स्टेट स्पेस लैंडस्केप भी बोला जाता है. इस डायग्राम को, it's a two-dimensional representation of state space with respect to or versus the objective function value. The maximum objective function value is the global maximum. So maximum where the objective function value is maximum is called as the point where objective function value is maximum is called as global maximum. Okay, and you will find out that there are local maximums as well, like a point over here. This is the local maximum. So if I see some neighborhood points in this region, okay, so there may be this point, there may be this point, there may be this point. Okay, although the diagram is continuous, you should consider that I have lot of neighboring states, and then I have joined them together to obtain a straight curve. Okay, curve कैसे obtain किया है? Say suppose this is the x-axis, and say suppose these are the points that I have for different neighboring states. So this is some s, say I. This would be then s of I minus some t. Okay, this is some si minus 2t, and same on the other side of the axis. So on the other side I will have si plus t, si plus 2t, that kind of a thing. Now I have projected, अगर मैं si minus 2t state में होता, okay, then this would be my objective function value. यहाँ होता तो ऑब्जेक्टिव फंक्शन का ये वैल्यू होता, यहाँ होता तो ऑब्जेक्टिव फंक्शन का ये वैल्यू होता, यहाँ होता तो ऑब्जेक्टिव फंक्शन का ये वैल्यू होता, यहाँ होता तो ऑब्जेक्टिव फंक्शन का ये वैल्यू होता. And what they have done is they have actually created a smoothed out line that passes through all these points. So maybe this is what they have done. Okay, so this is how they have arrived at this particular landscape. So ऐसी चीजें की है. This is the zoomed out version of maybe this. Okay, this is a zoomed out version of this. Okay, now consider that this particular locality of reference, in this locality of reference there is no point or no state that has, no neighboring state I should say, that has higher value of objective function than this point, right? This is the maximum value of the objective function in the locality of reference. Hence this point is called as local maxima. So If I were a agent whose current state is this and who is following the hill climbing algorithm, since I'm getting some increase in the value of objective function, I'll be always updating my current state with neighboring state till I reach this point. Once I reach this point, there won't be any neighborhood state that has better objective function value than me, and hence my algorithm would terminate. So consider what scenario I'm telling you. Say suppose this is the initial state, then my objective function value will guide my hill climbing algorithm to reach this point, and as I reach this point, now there is no state left or no way to go better than this particular state in the neighborhood states. Okay, please understand that there is this state Sj, but it is not in the neighborhood of this particular point. Hence, I won't understand whether I have reached the global maximum or I have reached the local maximum. My algorithm will always terminate in a local maximum. It will never go to the global maximum. So the optimization in such for such problem are always not achieved. Okay. Next thing is the shoulder. Now, if I am here in this portion of the state space, okay, anywhere in this portion of the state space, since it's a flat value for objective functions in the neighborhood, I won't be able to navigate over the tree. I won't be able to navigate over the tree because all the neighborhood states, they're having exactly same objective function values. So I won't be able to replace current state with any other state, and I will be stuck in a position where I am currently. So you can consider that I start at this point, I can navigate up to this point, and as I reach this edge point of this shoulder, so it looks like a shoulder, that's why it is called as shoulder. Okay, it looks like a shoulder. You can see your shoulder and you will understand what it is. Okay, if I am on my on this side of the shoulder, I can actually navigate towards this side by changing the neighborhood state with the current state up to when I reach this point. As I reach this point, I can't navigate this shoulder, although the shoulder is very small. See, I could come from this to this all the way by doing some replacement of current state to by neighbor state, current state by neighbor state, current by state by neighbor state. Maybe these are 10 replacements, and I may know that there are only 3 states. If I change my current state with the neighboring states, the neighboring 3 times, I would actually be able to navigate it. But being an algorithm, the algorithm will get stuck over here. So shoulder is also a problem in the navigation when it comes to hill climbing algorithm. Other issue with the hill climbing algorithm is a flat local maximum. A flat local maximum. So you reach a plateau point. A flat local maximum is also referred to generally as a plateau. Plateau manje pathar. If you are Maharashtrian, you know plateau means pathar. Platue. I'm not sure what is the exact spelling of it. Probably it is plateau. Plateau means a horizontal or a gradient-less region. So there is no gradient. Okay, the region doesn't accelerate or decelerate. It's a fixed value across the region for f function, that is the objective function. So these 3 issues are always there when it comes to hill climbing search. A general question many a times asked by many people: what is hill climbing algorithm? How it is different from the other algorithms? The hill climbing being a local search algorithm, it doesn't remember the path to the goal node. That's the first and foremost difference between hill climbing and all the other algorithms under the informed search. Another thing is it is also a kind of informed search, but it doesn't remember the path towards goal node. It only remembers reaching to the goal node. Okay, so that's the discussion about hill climbing algorithm. We'll stop our discussion today at this point. We'll see this diagram again next week, starting next week, and we'll complete hill climbing algorithm along with 1 or 2 algorithm we will be visiting, which is referred to as simulated annealing, which tries to better the hill climbing algorithm using certain concept from forging of metals. Okay, then we'll talk about genetic algorithms, which takes inspiration from the biological way of natural selection. Okay, and it tries to do optimization using it. This is also an improvement over the hill climbing algorithm. So what does all these algorithms do? They are all optimization technique, be genetic algorithm, be simulated annealing, be beam search, and be it hill climbing algorithm. All these four algorithms are nothing but optimization techniques, and these optimization techniques always help in problem solving related to not only AI problems which we are looking at, but also machine learning problems, deep learning problems. In neural network, we always try to optimize the value of loss function, minimize the value of loss function. That is what is our objective is, and that's why this function is referred to as an objective function. Okay, so this is a very interesting topic when it comes to actual use of AI in today's industry, but this is not that much important with respect to our current discussion. So we will not be going in detail